Two. After now? No.
Okay, folks, let's get started. Welcome back. Our first speaker today is Yasuhiko Yamada from Kobe, and he'll be talking about q-PVI, q-KZ, and the q-AGT relation.
Thank you for the introduction, and thank you for coming. So today I will talk about quantum Q on the Higgs equation and the q-KZ equation and the q-AGT relation. And this is based on the collaboration with 7 persons. That is the maximum of my experience. And Awata, Hasegawa, Kano, Okawa, Shakirov, Shiraishi. And today's talk contains a new result, which is obtained by the continuation of this collaboration. And the second paper will be, I hope, we can up in archive soon. First, I'd like to give a motivation and background of this work. The following relation between the isomonodromy deformation and two-dimensional conformal field theory is very well known for a long time. That is the classical limit of the conformal field theory is the isomonodromy deformation. And for example, the classical limit of the Virasoro algebra, here written in the operator product expansion form, and it is its classical limit is a Poisson algebra of the second of this type of Lax operator, which is common to the KDD equation and the family equation. And so it is natural to promote this classical relation to quantum version, namely the conformal field theory is equal to the quantum isomonodromy deformation. Moreover, due to AGT relation, there appears one more actor, that is a gauge theory. So we have 3 equivalent formulation of the same theory, that is a two-dimensional conformal field theory and a quantum isomonodromy deformation and 4-dimensional supersymmetric gauge theory. And the aim of today's talk is to show one concrete example of this relation in Q-deformed version. So the ordinary well-known relation is a differential case. And so we want to show one explicit concrete example in Q-deformed case. That is the motivation of this talk. So before going to the Q-deformed case, let us briefly review the differential case. So the correlation function of the two-dimensional conformal field theory satisfies nice linear differential equation, that is the BPZ equation. And here we consider the 5-point function of the Virasoro conformal field theory on Riemann sphere. So this guy. So we have 5 primary operators V located at 0, 1, lambda, infinity, and x. And when the last primary operator V tilde is a degenerate field of level 2, then it satisfies the second order differential equation. So this side is second order in the x variable and first order in lambda variable. And the coefficient A, B, C, is some definite rational function in variable lambda and x. And this is the most typical VPZ equation for the to the conformal field theory. And by tuning the gauge and parameters, one can rewrite this equation in various forms. And the first one is the Schrödinger equation for the quantum boundary 6 equation. That is this one. Here, the lambda is the time coordinate, and h is the Hamiltonian of the classical boundary 6. This is the Okamoto Hamiltonian, and this is a polynomial in Q and P canonical variables. And this one is a non-stationary Schrödinger equation with a time-dependent Hamiltonian. And this is can be considered as a quantum version of the boundary 6 equation. And equivalently, one can rewrite this Hamiltonian equation in the form, the so-called Innocentes model. And the relation between this guy and this guy is called Pan-Beccaro zero correspondence. And this form of the equation appears in the Charik's talk on first day. And so the VPG equation is related to the quantum boundary 6 equation. Okay? And the same equation can be obtained from the SL2 Knislnik-Zamolov-Chkov equation. And in this case, we will consider the 4-point function. And the equation can be written in this form. Here, theta is the Euler operator. Theta x is an Euler operator with respect to x, and theta z is an Euler operator with respect to z. And the standard form of the KZ equation is like this. And here the residue operator omega is a Casimir. And in this case, we like this operator in the differential form. So this is a Casimir operator acting on the two variables xa and xb. And if we write this residue matrix in this operator form, then we can consider the generic spin, generic complex spin. So we don't need to assume this j is an integer or half integer. So and in this setting we have 4 z variable and x variable. So we have 8 totally 8 variables. But there is a SL2C symmetry with respect to x and with respect to z. So effectively we have 2 variables. And using the cross ratio variable z and x, then one can rewrite this set of equations in a single equation in this form. And one can show that by some suitable gauge transformation and the parameter change, this equation is equivalent to the previous one, this one and this one. So in this sense, the 4-point KZ equation and 5-point degenerate VPZ equation is equivalent, and they are equivalent also to the boundary 6 equation. Okay? And this form of the equation can be regarded as a quantum version of the Zeiger-Witte curve. And this guy is nothing but the change of the parameters. And shortly, we will show that this equation has an explicit solution written in terms of the instant on partition function. So in summary, we have four equations: BPZ equation, quantum physics equation, Knittnik-Zamoshkov equation, and the quantum Zygowick-Karp equation. And all of them are equivalent with each other. Or in other words, these guys are the same equation with different interpretation. So, and we also have the explicit solution of these equations thanks to the AGT correspondence, like Iota-Tachikawa correspondence. And in our relevant case, the solution that is obtained from the gauge theory, four-dimensional gauge theory, with a SU2 gauge group, with four matter field in the fundamental representation, and one additional operator called the surface operator. And the result is written in this form. So the solution is a sum of two partitions, lambda 1 and lambda 2. And that is a power series in x and lambda over x. And here lambda 1 and lambda 2 is a partition which is striped in this way, white and orange. And this guy is orange, white, in this way. And the power of x is the number of the white box in this partition, striped partition. And the power of lambda over x is the number of the orange box on this partition. And the coefficients is given by the factorized form. And this n is the so-called orbifolded Nekrasov function. And the explicit form is given in this way. And here the bracket symbol is nothing but bracket z is nothing but z itself in this case. This is an additive version. And later we will consider the Shinchi version, that is the cube case. Okay? And the parameters here, U and V and W, are given by the parameter in the equation M and A in this way. So these equations have the explicit solution written in terms of the sum of the partitions. Okay. So this is the case of the differential case. So what we want to consider is the Q version of this story. And for the solution, the Q version is very easy. So that is obtained simply by replacing the bracket z to the Shinchi function. And this is a natural Q analog of the instant conversion function or chaos-theoretic function. So the problem is the equation. So we want to know the good equation satisfied by this function. And so we want to find the Q analog of these guys. So it is the equation, quantum physics equation, and the Zygowick-Karp and q-AGT equation. And except for the first one, there is already natural Q deformation of these guys. So the quantum Q physics equation was already formulated by Hasegawa-san more than 10 years ago. And quantum Zygowick-Karp, the Q analog of the quantum Zygowick-Karp is also known in several people. And of course, the Q deformation of the case equation is, of course, very well known. But the first one, the Q analog of the BPC equation, to find this guy is a very long-standing problem. The Q deformation of the Virasoro algebra was discovered a long time ago by Shiraishi-san and Shiraishi-Kubo Awatahodake. And after that discovery, more than a quarter century, we cannot find the equation satisfied by the correlation function of that algebra. The main reason is that there is no natural coproduct structure on the deformed Virasoro algebra. So, but very recently, 2 years ago, Shakirov discovered very nice difference equation, which is our candidate for the answer of the discussion. So, as I explained shortly, the Shakirov's equation looks quite different from the differential case. But nevertheless, it exhibits very nice properties as the correct Q analog of the BPC equation. And the main purpose of this talk is to explain this surprising fact. So this is the introduction. So the plan of the talk is that first I will explain the toy model, which is a miniature of the Shakirov equation. And that is our example on the usual q-AGT function. And in section 2 and 3, I will look at the Shakirov equation and formulate the main theorem about the solution of that equation. And section 4 and 5, we prove the main theorem using the relation to the q-KZ equation. And finally, I will explain some other nice properties satisfied by Shakirov's equation. Okay, let's consider a toy example. The essential ingredient of the Shakirov equation is the operator B, which is a linear operator acting on the formal Laurent series in variable x. So it sends x to the n to the x to the n with this coefficient. We consider q is absolute value of q is less than 1. So this is considered as a convergent factor. So, and this kind of operation also appeared in the Kedem-san talk the second day, and which is called the Cherezonics Gaussian in that talk. And more precisely, this guy is the Fourier transform of the Cherezonics Gaussian. So anyway, this is also played some integral system already. And usually, this operator we call Borel is used to get convergent series from divergent one. And such procedure is called the q-Borel transformation. So one may think, and I also think so that before, the Borel transformation works or useful only for the divergent series. But we learn that this operator also plays important, interesting role for convergent series. And let us see the simple example
Sorry, can I ask a question?
Yes.
You call this the q-Borel transformation. So it seems to suggest there's a non-q version, but it's not obvious from what you have at the top, because setting q to 1 is doing nothing, so that's clearly not what
So
what it is.
not usual non-Q Borel transformation is the operator that operation that sends x to the n to the x to the n over n factorial.
Ah,
That is the usual differential case
Okay.
Borel transformation. So this is not the natural Q analog of that guy, but the rho is the same. The convergent factor. And the typical example of the we consider it the Heine series. So everyone knows very well this series, the 251, and the coefficient is given by the q factorial. And this Heine series is uniquely characterized as the solution of this Heine's equation, which has a power series in x starting from 1. And this is a characterization of this series. And here the P is the q-shift operator. And we use this notation throughout this talk. And to see the structure of this kind of operators, it is useful to consider the Newton polygon. Here is the Newton polygon. The Newton polygon is usual Newton polygon of the Laurent polynomial. And in this case, we have non-commutative variable x and p, but we consider they are as commutative and consider Newton polygon. So in the Heine's case, we have x times degree 2 polynomial in p, and x to constant x to the 0 and degree 2 polynomial. So we have the Newton polygon of the Heine operator like this. If we consider the dual diagram of this Newton polygon, we have this kind of wave diagram. In gauge theory, this diagram can be considered as a five-grain wave or a tropical curve. Okay? And in this case, this curve is of genus 0. And later we will consider genus 1 curve. And by simple computation, we have this relation. So the multiplication x and the Borel transformation is exchanged in this way. And the shift operator p is commutative with p. Or in terms of the adjoint action, we have this relation. Adjoint of b acting on x is px, and adjoint b acting on p is p itself. And in terms of the Newton polygons, this adjoint action changes horizontal edge to the tilted edge. So this x is this direction, and this px is this direction. So this horizontal direction is tilted to this way by the adjoint action p. So, for example, this operator, whose Newton polygon is written in this way, then by adjoint action of b, this operator is transformed this way. So this 1 and p here is not changed, And this is x, correspond to x, which change it to px here. And this p over x change, move it to here. So, so in this way, in terms of the Newton polygon, the action of the adjoint action of the Borel is a kind of the theta theta. Okay. So, and in this talk, I will this kind of computation many times. And the important fact is that the Heine series can be characterized by this equation. So this is a very different characterization compared to the usual Heine's operator. So Heine's operator is a Laurent polynomial, but this is not the Laurent polynomial. And also the Heine's operator is additive structure, but this operator has a multiplicative structure. So the format is quite different, but this operator also characterizes this series. So to see this relation, the proof is given as follows. So this relation is a combination of these two equations. So if we plug this guy into here, then we obtain the previous equation. So to prove this equation 4, it is enough to these two equations. And the second one is nothing but the parameter change of the first one. So it is enough to show the first one. And to prove the first one, we use the theta total explained before. So we consider the adjoint action of this guy. This guy is the inverse of this operator. And we can show this relation. So adjoint action of this operator on the Heine's operator is essentially the same as the initial one. Only the parameter is changed in this way. And if we show this relation, then it tells that this function is also the solution of the Heine's equation. And this combination preserves the power series starting from 1. So this is also the Heine's series. So that is the strategy of this proof. And so the proof of the equation boils down to show this adjoint action. And to this relation, we use the adjoint action on variable p and x. So each factor, so we have the infinite product and the Borel inverse and the infinite product. And each factor, the adjoint action of each factor is nothing but the simple change of the p or x variable. For example, this adjoint action, this is the function of x. So the x variable is not changed at all. And the p variable is changed to the y minus x times p. And Borel action gives this. And the third infinite product, is this transformation. And combining this, we obtain this relation. So, so the computation is straightforward. So it will be better to see the diagram. So first, this is the Newton polygon of the Highness operator. And the first gauge transformation, we have here is the row of where the power of p is 1, and these guys are power of p 0, and these guys are power of p minus 1. And so, and here we have the coefficient is the degree 1 polynomial index. And by this transformation, the degree of this guy becomes 2. So we have one more factor. And alternatively, this part, the degree becomes 0. So this transformation moves this monomial here. So and then by the inverse Fourier transformation, this Newton polygon is transformed in this way by Theta. And then again by the gauge transformation, this factor moved to here, and we recover the original Highness operator, where the parameter is slightly changed. That is the relation, this one. Okay. So we learned that the Highness operator can be a very different characterization.
So what's the exact connection between this 5D theory and 5.1? Because like it's not a recursive function, it's just some kind of defect function for the 5D theory.
In the gauge theory context, this toy example is a boundary term of the Laplace function.
Right. Okay.
So we will consider in some sense a double of this story. So,
Boundary.
so the solution of the Shakirov equation is the power series in x and lambda over x. And if we take lambda zero limit.
I understand that. That's because of the that means that you have a Lagrange brain, you have a defect which inserted into the picture. But I don't see it in your formula. It's like only work with 5. I cannot.
I'm sure. So anyway, this toy example is a miniature of the Shakirov's.
No, yeah, that part I understand.
So here is the main object, the Shakirov equation. So the psi is the unknown function. That is a function with respect to lambda and x. And the t-shift of lambda is given by this operator. And we have two Borel operators here. And A1, A2, A3 is a function in x and lambda. Here the qt and t1, t4, q lambda, q is a parameter and lambda x is a variable. Then the small phi is a single infinite product. capital Phi is a double infinite product. So this is our main object of this talk, which is discovered by Yasuhiko 2 years ago. This looks a little bit complicated, but by some gauge transformation, one can reduce this equation in more simpler form. So first, relation is like this. So by the gauge transformation, which is by applying the third coefficient A3, and then the equation for W is simplified in this way. So in this form, we do not need the double infinite product. Only single infinite product we can write the equation. And more further, if we further gauge transform by this factor, then we obtain a slightly different form of the equation in this way. Here we use the relation between the double infinite product and single infinite product. And we also change some parameters by this rule. So we will consider the equation in this form. Of course, these guys are equivalent to the Yasuhiko's original equation. And in the following, the part of this operator, this part, the multiplication and Borel, the multiplication, Borel, and the multiplication, and this part played the essential role. So we put these guys as HS. And this operator is the main actor of this talk. So the first form, the equation for W, is convenient to see the relation with the quantum cube under 6 equation. So to make the computation easier, we put this part as H. So A is this part and B is this part. And for the time being, we omit this operator. So we consider the operator written in this way. Then by a simple computation, we can compute the adjoint action on variable x inverse and x inverse p in this way. So the adjoint action of this operator on x inverse is given this relation. Here, beta is the ratio of the shift of the function p. And here the alpha is the similar factor arising from function a. And in this case, a and b are the infinite product, or infinite product for each in the denominator. And if we write them in this way, then and also we put the variable f and the variable g, define the variable f and the variable g in this way, then this relation can be written in this form. And this is the Heisenberg equation, which arises from the Yasuhiko's equation. And in this computation, we did not consider this part and this shift part. And considering this part, these parameters will be changed by the discrete time evolution. So the Heisenberg equation arising from Shakirov's equation is a non-autonomous version of this transformation. And we can see that this equation is the quantization of the deformed Panov equation. So this equation is Jimbo Sakai's q-Panov. The form of this equation is the same as Jimbo Sakai's q-Panov 6 equation, which is a q-difference analog of the Panov 6 equation with P15 affine variable symmetry, and which is located here in the classification of the geometric classification by Sakai-san. So the equation arising from Shakirov's equation is the quantization of this one. And so in this case, the variable fg is defined in this way. It's a non-commutative variable. So in conclusion, the Heisenberg equation arising from Shakirov's equation is a quantization of the q-Panov 6 equation. And the quantization of the q-Panov 6 equation has been known for some time, more than 10 years ago, by Hasegawa-san. And he constructed the quantization starting from the representation of the affine variable. And in his construction, some theta function was used instead of the Borel transformation. And in fact, some operator variable theta function and Borel transformation have the same adjoint action on variable x and p. So one can also use the theta function instead of the Borel p. So in fact, the adjoint action of the theta inverse is, by definition, it's in this way, and using the commutation relation between p and x, is the p here is changed to p, and using the theta function property of the theta function, this can be reduced to this guy, and we obtain this. And this is nothing but Borel action on operator x. So this one and this one, Borel b and this theta inverse have the same adjoint action on variable x. And of course, these two are trivial action on variable p. So this combination and this Borel has the same adjoint action on variable x and p. And previously, Hasegawa-san used this kind of operator instead of Borel. So in this sense, the adjoint action or the Heisenberg equation is same for the Hasegawa's operator and the Shakirov's operator. But if we consider the Schrödinger equation, there is a crucial difference. So if we consider the Schrödinger equation, where the wave function is considered as a formal power series of x, then the Borel the action of the Borel operator is very natural, but the action of this guy is not too easy to handle. So for the study of the solution, this Borel operator is good, better than this theta function. And we will consider the solution in terms of the Shakirov's formulation. So we start this equation. So we have two Borel and multiplication operator here. And one can solve at least part of it using computer. One can solve this equation in power series in x and lambda over x. So we fix the normalization as the first term is equal to 1. And the second one is ij equal 1, 0 or 0, 1, 2. And the coefficients are given by this factorized form. And the next reading term is a coefficient where ij is 2, 0, 1, 1 or 0, 2. And the coefficients are given in this way. And 2, 0 terms are coefficients are factorized. And 0, 2 terms also coefficients are factorized. But the 1, 1 term, the coefficient of the 1, 1 term is rather terrible. And if we write some factorized form, we have 3 terms. If we expand this guy, the expression is very huge. So anyway, the one can solve this equation level by level, mathematically, and then the coefficient Cij will quickly become huge. And here is the number of the coefficient for each time. So we see a space, we see the part here. So some coefficient is a single term of factorized form, but this guy has 3 terms. And other power, so we can solve the equation from starting here, and next we determine this guy, and next we determine this guy. And so we can solve in this direction. And the terms will be, number of terms grows very quickly. And these numbers is given by the expansion coefficient of this series. So, x to the I and q over z to the I and q over z j coefficient of this infinite product gives a number, these numbers. And this infinite product is a product of the character of Padan module of U1 affine algebra and SH line algebra. So, this structure seems to suggest some toroidal nature of the system. And each terms has a factorized form. We can observe by computer experiment, and which is exactly the form obtained by orbifold Laplace function, which is nothing but five-dimensional analog of the previous differential case. So we want to prove this structure. So the main idea is to use the q-KZ equation. So in the some special specialization of the parameter d, so we take d2 to the q to the power of minus m, and d3 is equal to the q to the power of minus n, where m and n are positive integers, non-negative integers. Then the action of the Shakirov operator on the monomial has finite support. And so we have a finite size of the matrix for the action of this operator. And for example, the most simplest case, the Mn is 1, 0, then we have the 2 by 2 matrix, and whose matrix element is given in this way. And this is the R matrix of the UK center. So in general, we can compute the matrix element of this expansion by using the definition, and we skipped the details, and the final equation is boiled down to this relation. And if we specialize the parameter to some integer, then we obtain this relation. And this relation is nothing but the connection problem of the degree n polynomial. And this kind of characterization of the R matrix or the Q6J symbol was studied by Rosengren in 2007, and the same equation arises from Shakirov's operator. So by using the computation given here, one can obtain the explicit form of the coefficient matrix R, and which is nothing but R matrix of UQSM2. So some specialization of the Shakirov operator is the q-KZ equation. Okay. So next we want to show the Jackson integral solution of the q-KZ equation is a specialization of the Laplace partition function. And to see this, we use the result by Ito-san. In his formulation, the solution Jackson integral solution of the q-KZ equation relevant for this case is given in this way. Here, this is not the double infinite product. This is the so-called master function in the integral representation. And then the phi is given in this way. And C is the cycle of the Jackson integral. And phi is the cocycle factor inserted into the integral. And the important fact is that we have factorized the form in this way. So if we sum in over this I is the subset of the n, and if we take the sum over I, then we obtain the completely symmetric function with respect to the integration variable z. But the important thing is we do not take this sum. Then we still have the factorized expression of the summand. And in this form, we can compare the integral representation and the Roman partition function. And using the Ito-san's result for the q-KZ equation relevant for this situation, we find that Jackson integral solution obtained by Ito-san and the long partition function is exactly coincide by term. The factorized expression is equal with each other. So in this way, we can prove the specialized Shakirov equation is nothing but q-AGT equation, and its solution is given by the overall necklace function. That is our main result. So we have some other result on the Shakirov equation that we omit today, and so give the conclusion. So we show that the Shakirov equation is a quantum version of the q-P6 equation, and it can be reduced to the q-AGT equation. And the explicit solution can be obtained by the affine long partition function. And the future works, expected future works is to consider the, of course, the elliptic version of this story. So anyway, thank you very much.
Naively, for me, the Shakirov equation also looked very, so from non-expert point of view, this also looked very much like the equation for the non-stationary Rusinas model. And I'm wondering, and my question is there a connection between Shakirov's equation and non-stationary Rusinas? Yeah, rank one, one variable non-stationary Rusinas.
So the Shakirov equation has a conserved quantity, which is written in this form, or the Newton polygon given in this way. So this is a quantum point equation. So there may be another formulation of we have Zaga-Witten curve and DPZ equation, and they are equivalent in the differential case. But in Q case, they are different. So the time evolution operator and the conserved quantity is equal in the differential case. But the Q difference case, they are different. And the conserved quantity is the q-point operator. And its eigenvalue problem will be related to the Rusinas operator, I think.
Other questions? Okay, I know it's complicated, but what about higher rank?
I didn't consider the higher case maybe. Oh, yeah.
Okay, there are no more questions. Let's thank the speaker again. Back at 3:15.
I have kind of a A-type. Actually, the direct radar you show
Very
Yes, we met on. Nice to meet you. Yes, nice to meet you. Oh, very nice.
Thank you. Actually, 10 years ago, I have constructed quantized difference QP6, but after that, I couldn't find that kind of let's say Q-Borel transformation to make it complete on the functions. So I threw it away for some time.
But now everything came together.
Yeah.
Yeah, wonderful. I also admire how you could put all this together.
Maybe it is partly because of the COVID flu. So
this is true. By COVID, what we all learned to talk and see.
So we can do the joint work by the Zoom. So
that is true.
Otherwise we can't.
Yes. And it seems, you have all people together that you could do this.
Kind of, interesting. So it's a byproduct of the, staying home policy.
Yes. Bad things can have good path. Nothing is black and white.
Right. So second one will appear soon.
With you updates. So you met every week? You had a fixed time?
Basically, Saturday afternoon.
Saturday.
Because one has to look more about the whole structure.
So Shiraishi-san is the initiator of the joint.
So he was.
Yes.
So this is the hallmark.
So he's a great leader of us.
He was.
I would have to look at it.
Now we hear more.
I mean, if you only have one paper, you have only one paper in that journal.
Now you're
okay, but I can find.
So you went out together?
So actually, this is my first time since 4 years ago to come to Tokyo.
It's also for me the first long flight.
Yes, I know.
So how did you fly from Europe to Tokyo? You can't fly over the Russia.
No, it happened. I had no trip at all, and the week before this, my postdoc supervisor in Canada. So he accepted the Thursday meeting, and there I had it. I wanted to go, and so I went first to Montreal, and then there was the meeting, and then I came to Tokyo. So it was, for me, it's a very interesting trip. So we go around. I will see how I like it.
So otherwise you have to fly to Dubai or Singapore or somewhere.
I will fly back to Bangkok.
I see.
And then Bangkok. It'll be a long flight. I will
Maybe to take more years to stop the war.
Formula
Yeah, it doesn't sound so.
We would have enough problems with climate. We don't increase problems. We all need to work together. Fight each other.
Maybe in someday, maybe every kind of flight should be cancelled because of the warming.
Yes.
I don't know.
We will travel much less. I think.
Yeah,
Oh,
yeah.
okay, yeah.
It's become very expensive. Also.
Right. So shake hands.
Yes, otherwise only two. Shake hands.
トータルナンバーオブインテグレーションがある。
Yeah, so we're integrating on RT.
No, it's very nice. I know your papers and so on, and now to see the real person and talk is very special.
Yeah. Thank you. So to our regret, Nomi-san is rather ill, so maybe we will.
Yeah, I know him, of course, very well. Yes, I know.
They say that he appeared here only in
Yesterday he
the
was here. I met him yesterday.
Oh, really?
He came.
Oh,
It was very nice. It was very happy.
oh, okay.
So there is a kind of
Yeah.
Some medicine is now appearing good to him, so maybe
Treatment
he will heal. Yes, it was actually a surprise. So, yes, he is, you know, he's a great mathematician. So,
Yeah, and a great person.
yes.
He is so good. He can make things happen.
Right. Yes.
When he was in Sweden, he succeeded that I worked with Yalma and Martin. He was helping that was appeared.
This is SLN.
Okay.
Yeah, hope to see him soon.
One variable case
Active.
corresponding to SL2.
Yes.
So large and
Yeah.
then
Yeah, thanks.
only this.
Only that. Then it should probably no. Okay, I have to look at the details. It's too much notation to immediately recognize. Yeah, no, I can certainly sure, yes. Especially, yeah.